Hey, good morning, good afternoon. Today, we are going to look at the application of the mole concept in a slightly different way. We're going to look at something called hydrates, okay? It's another type of problem that we will learn to solve utilizing the concept of the mole. All right, so share your screen, make sure you have your periodic table and your calculator present. You need to take these notes with me. You need to be an active listener, actively participate. If there is something that you have a question about, come on, then you need to put a star by it. All right, and bring it up in class. Getting there. Took a little while. Okay. So, guys, this is hydrates. I'm calling this topic 5.7. All right. You know what I'm going to do? I'm going to erase that and I'm going to put some lines on this piece of paper. Paper lines. Okay. Now, hydrates. It helps keep my notes a little bit neater. I like it better. Okay. What is a hydrate? Well, what does the word hydrate make you think of? Hopefully, you're thinking water, right? Hydrated, dehydrated. So a hydrate for us is a solid compound. For us, this will be a salt or an ionic compound, okay? So we're going to have a solid ionic compound that also has H2O molecules in it that contains a certain ratio of H2O molecules to formula units. Okay, so what we have here is a solid. We have a shiny, solid, crystal-like hydrate. Okay, so if I could continue to share my screen, I attempted to get this picture in here, but I couldn't. But you see how this is a hydrate, okay? However, this is a hydrated mineral, not a hydrated compound, so it's not as pure. These are hydrated compounds. Notice that they are shiny and crystal-like, okay? I want you to keep that in mind. There's another hydrate. Look at that pretty color. That must have manganese, I would imagine. Or no, that's got cobalt in it. Look how pretty that is. Cobalt is chloride. It's hydrated. So what gives it that shiny appearance are the water molecules that you're seeing in there. Well, you're right, but it's still solid, okay? But there are H2O molecules in there. Now let's go back to our notes. What we need to look at is naming hydrates, okay? And it's real simple. We will use the 1 is mono, right? The 2 is di, the 3 is tri, the same as when naming covalent compounds. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca, the same prefixes that you use for polygons in your math class, right? And the same prefixes we use for identifying the number of atoms in a molecule, a covalent compound. So look at my example. Let's see, we have CuSO4.5H2O. Or let's have MgSO4.7H2O. Okay, this is what a formula for a hydrate looks like. Okay, you have this symbol, or you have the compound formula, actually. Compound formula. You then literally just put a dot. It doesn't mean by multiply, it's just a dot. And then you will have a number, and then you will have H2O, right? That's your generic formula. This number represents the ratio of H2O molecules, right, to formula units of the salt. Right? So what do I mean by that? I mean that for the first one, there are 5 H2Os for every 1 copper 2 sulfate, right? And for our second hydrate, we see that there's more water. There are 7 H2Os for every 1 MgSO4 formula unit. Okay? Now, how do we name this? We were talking about that, but we didn't finish it. We're going to name the compounds. This is really easy. I'm making it too hard. So that here is copper. Copper needs a Roman numeral. Its charge was a 2 sulfate. And then we will use the appropriate prefix. And because we have 5, our appropriate prefix is penta. And then add the word hydrate. Okay? So we have copper 2 sulfate pentahydrate. And yeah, that tends to come in one word. Okay? There you go. Let's look at the next one. This here. Let's see if that's a good color. Yeah, that works. Let's go with this pretty color. Right? This here is magnesium sulfate Hepta hydrate. Okay, so in order to turn that around backwards, I'm going to use this blank space up here. Okay, guys. If I'm going to write the formula, you might want to just continue your notes down. Okay. If I'm going to write the formula, I would see something like this. Manganese 2 chloride dihydrate. Well, that's easy. Manganese 2 chloride is MlCl2. Dot di is 2. Hydrate is H2O. All right, so you just take what we've learned and add a dot H2O with a number in front of it, okay? Now, the next thing you need to wrap your head around is how can you mathematically determine the formula of a hydrate? You calculate it, you figure it out, all right? How to determine the formula of a hydrate. Well, think about it. All we need to know is the ratio, right? All we need to know is what this ratio is. Let me find a better color here. We need to know what this ratio is. Right here, we have a 1:7 ratio. Right here, we have a 1:5 ratio. That's how I knew to put 5. That's how I knew to put 7. Up above here, we have a 1:2 ratio. So in order to determine the formula of a hydrate, I simply need to know how many water molecules per salt, formula units of salts. So what I will do is I will take the moles of water and divide it by the moles of something called the anhydrate. let's talk about that real quick. So you are in, how are you going to get these numbers? Those of you that come to school, there's a good chance I'm going to let you do this in the lab, or I'll collect the data, we'll share it, we'll see how that goes. But you're going to take your hydrate, okay? And what you're going to do is you're going to set up something called a ring stand, okay? These are the things we would have been working with. And it's a stand on your lab bench, all right? This is your lab bench. And on your ring stand, you would attach something called a ring, all right? And in that metal iron ring, you would place something called a crucible, okay? Crucible can withstand an awful lot of heat. Underneath that crucible, you would place your Bunsen burner, all right, which would be connected to a gas source, and it would be lit, and it would provide some heat. And remember, in here, you have a hydrated compound. You have a solid compound that contains water, and you are heating it. So you are heating something that contains water. When you add the heat, what comes out of the hydrate? Water, right? Let me change my color here. Let me go back to this. We're going to, I'm going to actually make this a little bit bigger. We're going to add, come on, we're going to add heat that's going to drive the water out of the hydrate, and we now have something called the anhydrate, right? So we have the hydrate equals the water and the anhydrate. This is the compound without the water. So, right? And we have a law of conservation of mass problem, right? Let me erase this and rewrite it, and rewrite this, and I'm actually going to rewrite this. So we take our hydrate, we add heat, we get water, and our anhydrate, okay? Now, this is a law of conservation of mass. Mass hydrate equals mass water plus mass anhydrate. It just makes sense. A law of conservation of mass. If we started with 5 grams of this, and after we heated it and the mass stopped changing, we had 3 grams of this, then we know that we lost 2 grams of water. And if we apply that, we can easily figure out the moles of water, the moles of the anhydrate, divide them to figure out the number, the ratio that represents the ratio. So let's look at some problems that are similar, like what you'll look at. A hydrate of magnesium sulfate, that's MgSO4, has a mass of 1342. So our hydrate has a mass of 52 grams. The sample is heated. Okay, we're heating it. And we know that at that point we will have water and MgSO4 without the water. Let me rewrite that. All right. Okay, let's read. Until no water remains, the water has exited the system. The magnesium sulfate anhydrate has a mass of 6.60. So this is my anhydrate, and this has a mass of 6.60 grams. Well, I have a certain amount of water equal to, so I can easily solve for the mass of water that must have left the system and caused the decrease in the overall mass. So that's 13.52 minus 6.6 equals, and I can easily determine that I had 6.92, or there were 6.92 grams of water in the hydrate. Remember, I'm trying to figure out the formula and name. So I need to know what that number is, right? And we said that the number is equal to the moles of water divided by the moles of anhydrate, okay? Now, let's get our moles of water. You need to label everything. It really makes your work a lot easier. Oh, look, I have grams of water. So let's take my 6.92 grams of water. Let's turn the grams of water into moles of water. 1 mole is 18.02 grams. So 6.92 divided by 18.02 equals 0.384 moles of water. Okay, so I now know this number here. Okay, but I need to get the number on the bottom. I need to get my moles of anhydrate. Well, look right here. I've got 6.6 grams of the anhydrate. And what is the anhydrate? Oh yeah, it's magnesium sulfate. So I have this many grams of magnesium sulfate. I need to convert the grams of MgSO4 to moles of MgSO4. All right. So I'm going to add up the molar mass of magnesium sulfate. Magnesium is 24.31 plus sulfate, which I'm pretty sure is 32.06, plus my 4 oxygens, which is 120.37. Sounds right. Now I'm going to divide 6.6 divided by that answer, and I'm going to get 0.0548. 0.05483 moles of my anhydrate. If I take those and divide them, I hope that I get a very pretty whole number. And if I do not, then I know that I've done something incorrect. Beautiful. I get 7.00. Okay, so let's answer the question. The question was, what is the formula and the name of the hydrate? Well, it is MgSO4.7H2O. That is magnesium sulfate, Hepta, sorry guys, let me fix that, Hepta hydrate. There's my answer. Okay, so you want to be particular with your values because once again, you're looking for very good whole numbers. So you don't want to do too much rounding. Let's look at another one, and I'm going to tackle it a little bit more quickly and see if you could, right? Okay, so when 5 grams of iron 3 chloride, so I've got iron 3 chloride hydrate, right? This is my hydrate, and I have 5.00 grams of it, is heated, I get 2.00 grams of water. It's telling me that are driven off. Okay, what's left over is the FeCl3 anhydrate, right? We took the water out. That's now anhydrated. We do not know how many grams of that we had, but we can easily see that 5 equals 2 plus x equals 3.00 grams. Grams of what? FeCl3 anhydrate. We need to know the formula, so we need moles of H2O divided by moles of the FeCl3 anhydrate. The moles of H2O I will get by taking my mass of H2O and turning it into moles. So I've got 2.00 grams of H2O, I know that there are 18.02 grams in every 1 mole of H2O. All right, 2 divided by 18.02 equals, that's 0.11, 0.11. Now I've got an 098779. Those are all big numbers. Let's just go 78. Okay, moles of H2O. I now need to get my moles of iron 3 chloride. So I'll get the anhydrate, right? This would look like that if we're being consistent. So I will take my 3.00 grams of my iron 3 chloride. I will convert my grams of iron 3 chloride to moles of iron 3 chloride. 1 mole. Iron is 55.85 and chlorine is 35.45 times 3. So I've got 162.20. When I get my moles, I'll do 3 divided by that, and I get 0.018495. I'll make that a 6. What I'm going to do is divide these two values right here, okay? I've got my moles of H2O divided by my moles of my anhydrate. Oh, good. And once again, I got a really pretty whole number. I got a 6.00. So I must have an iron FeCl3.6 H2O, and that is iron 3 chloride. 6 is pentahexa hydrate. Boom. Okay. Notice you could get the percent composition of this, right? Percent water would be the mass of the water divided by the mass of the entire thing times 100. If I had a ratio, I could determine, you know, if I only had, I now know, right, that for every 1 mole of these, there's 6 moles of these, or 1 formula unit, there's 6 formula units. So if I had half a mole, I would have 3 moles of water. So I can use this to solve other problems, okay? Great job, guys. Well done.